This is the 7th video in our series about Lie algebras, and the main goal for today is to prove something called Engel's theorem, which will require us to prove some lemmas as preparation. But before we look at those lemmas, let's look at, well, this big goal, which is the proof of Engel's theorem. So let's suppose we've got L, which is a Lie algebra and also a subalgebra of GLV, where V is a finite dimensional vector space. It also satisfies the condition that every x in L, when viewed as a linear transformation from V to V, is nilpotent. So since L is a subspace of GLV, we know that everything inside of L can be thought of as a linear transformation. This isn't true of all abstract Lie algebras, but it's true in this setup. Okay, so if those are all nilpotent linear transformations and we're inside a Lie algebra, then there is a basis B of V such that every element of the Lie algebra, when written as a matrix in that basis, is strictly upper triangular. So the important thing here is that this happens for every x within the Lie algebra. So you may have learned in a linear algebra class that if you have a nilpotent linear transformation, you can always find a basis where it's strictly upper triangular. Well, this is stronger. This is if you have a Lie algebra of nilpotent linear transformations, all of them can be expressed as strictly upper triangular matrices. Okay, so speaking about that result from linear algebra, we are actually going to start our video with the proof of that. So let's see it stated a little bit more carefully. So let's say that V is an n-dimensional vector space and X is, well, put shortly, an endomorphism of V. So in other words, it's a linear map from V to V. We're also assuming that it's nilpotent. Then there exists a basis B of V such that in that basis, this X is represented by a strictly upper triangular matrix. So this is for a single linear transformation, not for a Lie algebra of linear transformations like this over here. So this is much, much, much weaker. Okay, so let's get to it. So since X is nilpotent, that means that there exists some natural number n such that x to the n is the zero map. Well, so that's the definition of a nilpotent linear transformation, is that you can exponentiate it to the zero map. And now what we want to do is take a non-zero vector V within V, but let's notice that that means that x to the n evaluated at V is equal to 0. Well, why is that? Well, that's because x is nilpotent, and x to the n evaluated at any vector is 0. Okay, so now what we want to do is let m, which is a natural number, be the minimum such that x to the m times, or evaluated at V, is equal to 0. So notice that since n is a natural number, well, that means we can easily list powers of x here. So we've got x evaluated at V, x squared evaluated at V, x cubed evaluated at V, all the way up to x to the n evaluated at V. We know x to the n evaluated at V is equal to 0, but we may have chosen V so that x to the n minus 1 evaluated at V is also equal to 0. So the idea here is we make a list of all of those vectors. X of V, x squared of V, x cubed of V, all the way up to x to the n of V. And we pick the smallest power of x that when we evaluate it at V, we get 0. Okay, good. But let's notice that that means that x to the m minus 1 evaluated at V is non-zero. That's just by the minimality of that number m. And I'm going to assign that the letter W. But notice, if we assign that the letter W, we have 0 is not equal to W, but x evaluated at W is equal to 0. But what does that mean? Well, that means that the null space of x is not equal to just the 0 vector. Why? Well, because W is within the null space and W is not the 0 vector. So in other words, we found a non-zero vector inside of the null space of x. In other words, inside of the kernel of x. Okay, great. So let's maybe take that little fact and then we're going to move on from there. So far what we've done is constructed a non-zero vector W that's in the null space of x. In other words, the kernel of x. But what that really means is that x evaluated at W is equal to 0. Well, and W, like I said before, is non-zero. Okay, great. And now we want to continue towards our goal of finding a basis that makes the representation of x strictly upper triangular. And we're going to do this by induction on the dimension of V. So let's notice that if n is equal to 1, that means that V is simply equal to the span of any of its non-zero vectors. But W is one of its non-zero vectors, so V is equal to the span of W. But let's note in this case that the matrix representation of x in this basis, which is just this single vector W, is the 0 matrix. So there's really nothing to do there. But the 0 matrix is the only 1-by-1 matrix that's strictly upper triangular, so we're done in this case. Now let's move on to the induction step, which begins with the induction hypothesis. So let's suppose the statement is true for any k-dimensional vector space. And then we want to suppose that the dimension of V is k plus 1. Okay, so that's our setup for our induction step. Okay, and then, well, throughout, W is in the null space of x, so we don't really need to rewrite that. But what we will do is introduce a little bit of notation. So let's set capital W equal to the span of little w. So this is a one-dimensional vector subspace of V. And then note that V mod W, that's a quotient vector space, is k-dimensional. So this is k plus 1 minus 1 dimensional. So that's because a quotient vector space is always the dimension of the top part mod the dimension of the subspace. So that's k plus 1 minus 1 dimensional. And then we want to consider the following diagram. So on the top, we've got this map from V to V, which is x. And then we have the projection map, which I'll call pi, which goes down to this quotient vector space V mod W. And that's happening at both ends here, so V mod W. And then here we want to complete this diagram with something that I'll call x bar. And we're completing this diagram so that it so-called is a commutative diagram. So in other words, x bar is equal to pi composed with x. So in other words, x bar on V plus W is equal to x of V plus W. So remember, everything in V mod W is a coset. That's why I've written it like that. Okay, so now let's partition this picture off to the side, and then we can, work towards that. So let's apply the induction hypothesis to V mod W. So that's something that's totally possible because V mod W is k-dimensional. Okay, so that's going to give us a basis, which I'll call B bar, which is V1 plus W all the way up to VK plus W. And this basis has the property that x bar represented in this basis is upper triangular. Great. So again, that's just applying this induction hypothesis. But what does that really mean? So that means we have the following maybe fact about how x bar acts on these basis vectors. So it goes something like this. For all j, which is between 1 and k, we have x bar evaluated at vj plus w is only going to depend on the v's that are like v1, v2 up to vj minus 1. That's maybe the technical way of writing down this upper triangularity. So in other words, we have this as alpha 1 v1 plus all the way up to alpha j minus 1 vj minus 1 plus w, where I guess kind of like I've done the coset addition off the board there. And now we're ready to build this out to a basis of the entire vector space. So let's do that here. So let's set b equal to our vector w, and then v1, v2, all the way up to vk. So over here, these were cosets, but here we just take a representative for each coset, maybe the representative that we're using right there. And then notice that we have this rule right here, x of w equals 0, which means that we have upper triangularity at the w position. And then because of this rule right here, that x bar evaluated at v plus w is x bar of v plus w, that means that x evaluated at vj will be equal to alpha naught times w plus alpha 1 times v1 added all the way up to alpha j minus 1 times vj minus 1, like that. So again, that follows from this action right here of x bar on the coset and this way that we defined x bar over here. So notice we have the possibility of having a term related to w, but I guess that's related over here to this coset because this term over here with the w in it is definitely inside of, well, this subspace. But notice that this is the property of being upper triangular. If you think about now the w being the first basis vector, the v1 being the second, and so on and so forth. So in the end, well, we've done it. We have the matrix representation of x in this basis B is strictly upper triangular. Great. So that's the proof of this lemma. Let's move on to the next prep result. Now for our next preparatory result. Let's suppose we have a non-zero vector space and a Lie algebra L, which is a subalgebra of GLV. So that's the Lie algebra of linear transformations on V. And then that Lie algebra L satisfies the following condition. So every x in L is nilpotent as a linear transformation from V to V. Then the result is that we've got a non-zero vector V inside of V such that x of V is equal to 0 for all x in L. But notice that can be restated as the intersection over all x in L of the null space of x is non-zero. So in other words, the kernel, if you want to think about it like that. Okay, great. So we're going to do this by induction on n, which is the dimension of L again. Starting off with the base case, which is the dimension of L is equal to 1. In other words, we can write L as the span of x. But let's notice that if x is a nilpotent linear transformation, then we can find a basis where it is written in upper triangular form. Then we can apply that first part of the proof of the last lemma to get an element of the null space of x. So let's just write it like that. So let's find a v in V such that x of V is 0, but then V is non-zero. So again, that's possible. Remember we did that before by looking at the minimum power of x evaluated at some vector, which was 0. Okay, So now let's move on to the induction step. So let's suppose that the statement is true for all Lie algebras of dimension up to k. So this is maybe like a strong induction hypothesis if you want to think about it like that. And then next, let's suppose that the dimension of L is k plus 1. So again, we're assuming that this statement holds if L is 1-dimensional, 2-dimensional, 3-dimensional, up to k-dimensional, and then we're looking at the next spot. Okay, so now we're going to make kind of a technical claim here, and that is there is an ideal I of L such that the dimension of I is k. So in other words, if L is nilpotent, we can get an ideal that has dimension 1 less than the dimension of the whole Lie algebra. So this is a pretty special thing happening already. So let's see the proof of this claim. So let's let A, which is not equal to L, be a subalgebra of maximum dimension. So you can just look at all possible subalgebras of L and pick out one of them that has the largest dimension. Notice that you could have more than one with maximal dimension, but we'll take one of them with maximal dimension. And then we're going to play the game of moving in and out of the quotient space. It's kind of similar to what we did in the last proof. So let's consider the quotient vector space, which is L mod A. So notice I didn't say quotient Lie algebra because at the moment A is simply a subalgebra of L. It may not be an ideal of L. And then also consider the following linear map. And this linear map is occurring on this quotient vector space. And I'll call it maybe add with a bar over it, thinking about the adjoint action. So it's kind of named appropriately for that. And what it does is it takes an element from A and sends it into GL L mod A. So L mod A is a vector space. So how does this map work? Well, it's going to go like this. So it's going to take an element A from A and it'll send it to the adjoint action of A on the elements of L mod A. So in other words, we have the following thing explicitly. So add bar of A evaluated at x will be bracket AX plus A. So that's what's going on inside of this GLL mod A. Okay, so now let's see what structure this map has. Okay, so let's see where we were. We had this maximal dimension subalgebra A of L. And then we built this linear map, which we called add bar, and it went from A to GL L mod A. So that means it needed to take elements of A and produce linear transformations from L mod A to L mod A. That's why this is like kind of crazy here. So if you want to think about it, add subscript A is really what we're getting when we evaluate add at A. And this, like I said, is a linear map from L mod A to L mod A. So that's what's happening. So in order to understand this linear map, we need to evaluate it at an element of L mod A. And so what it does is it takes, well, I wrote X on the last board and I've written X here as well. But what it's really doing is taking a coset, so add a bar of X plus A, and it's sending it to the coset bracket AX plus A. Okay, so that's where we are at the moment. And now we're going to make the following claim about the structure of add bar, and that is it's a Lie algebra homomorphism. So add bar is a Lie algebra homomorphism. So notice A is a Lie algebra because it's a subalgebra of L, and GL of any vector space is also a Lie algebra by, some stuff that we've talked about, the whole course. Okay, so let's see how this might work. we need to look at the bracket of add bar A with add bar B. And in order to know what that's doing, we need to evaluate it at x. But observe that that's going to be add bar A, add bar B, minus, well, the difference in the other order. So add bar B minus add bar A, and then we evaluate this at x plus A. I keep forgetting that this should be a coset here, so that's x plus A. Okay, but now let's work from the inside out. So this is add A, evaluated at, let's see, bracket bx plus A, minus add B, evaluated at bracket AX plus A. But then unraveling that more, that'll give us, let's see, bracket A bracketed with bracket BX minus the bracket of B with the bracket of A with X plus A. Again, that's just unraveling this map more. But now we can apply the Jacobi identity. So let's say that this arrow is applying the Jacobi identity to this difference here. Now it's maybe not the Jacobi identity written the way that we write it when we write the definition of a Lie algebra, but it's an equivalent formulation where we've also used the alternating condition on the bracket. And then that'll allow us to write this as the bracket of AB with X, well, plus A. But that's exactly add of the bracket of AB evaluated at X plus A. But that's exactly what we need for this to be a Lie algebra homomorphism. So we've got this claim proved. Okay, we just got done showing that that map was a Lie algebra homomorphism. But once we've got a Lie algebra homomorphism, we can use some things that we proved about Lie algebra homomorphisms. First of all, we're going to use the fact that any image of a Lie algebra homomorphism is a Lie subalgebra. So let's maybe introduce some notation for that. I'll call that A tilde, which is the image of add bar. So in other words, it's the image of this Lie subalgebra A within GLL mod A, based off of this map that we worked with on the last board. Okay, so like I said, this is a Lie subalgebra of this GLL mod A Lie algebra. Okay, so note that the fact that this is a Lie subalgebra are actually simply the fact that this is a vector subspace gives us the following like inequality of dimensions. So let's notice that the dimension of A tilde will be less than or equal to the dimension of A. That's because it's the image of A, and whenever you take the image of a vector space, the dimension can only stay the same or go down. It can't like get larger. Okay, but then that is going to be strictly less than the dimension of L, which is equal to k plus 1. We know it's strictly less than the dimension of L because we chose that to be a subalgebra, which was not the entire Lie algebra. That was an important thing. So we pointed that out when we said it for the first time, but maybe let's highlight it by putting a not equal to here. But now let's notice that by this strict inequality here, we actually have the dimension of A tilde is less than or equal to K. So that means that we should be able to apply the induction hypothesis to it. But we want to get to the point where we can apply the induction hypothesis, which means we need every element of it to be nilpotent. But how do we do that? So here's something that we know. We know A in A is nilpotent, and that's simply because A is a subalgebra of L where everything is nilpotent. But then if A is nilpotent, the adjoint map defined by A is also nilpotent. That's by something we proved in the last video. But from that, it follows that add A is nilpotent. And this is viewed as the map associated to A within GLL mod A. But this is done for any A within A, and every element of A tilde is a descendant of something inside of A. So in other words, A tilde satisfies what I'll just call the hypotheses of our lemma up here. Not only does it satisfy the hypotheses, but it also satisfies the hypotheses of the induction hypothesis due to its dimension being less than or equal to k. So that means we can apply the induction hypothesis to this map or this subalgebra A bar. And what that will do is get a non-zero element, which I'll call y, inside of L mod A, which means it actually should be a coset y plus A inside of L mod A, such that we have add A bar of y plus A is equal to 0 for all A within A. So again, that's by the induction hypothesis being applied to this subalgebra A tilde. But now let's see what this statement here actually means, because that statement, which I've underlined in pink, is actually very, very powerful. By the definition of this map here, that means that the bracket of A with y plus A is the 0 coset inside of L mod A. But this happens for all A in A. So let's write that. So for all A in A. But something being equal to the 0 coset means that you're in the subalgebra. So in other words, the bracket of A with y is inside of A for all A inside of A. But now we've got this string of inclusion, which is nice. And that's going to start on the left with A, which is going to be inside of the direct sum of A with the one-dimensional subspace spanned by y. So I'll just write that as Fy, where F is the ground field. We could also write that as span y if we wanted to. But in turn, that's going to be a subspace of L. And also, we know that we do not have equality right here. We know that we don't have equality right here because since y plus A is non-zero, that means that y is not an element of A. But look at this. This is a subalgebra of L, which has dimension larger than A. But A was chosen to have maximal dimension. So since A was chosen to have maximal dimension, that means that these two have to coincide. Otherwise, that would contradict the maximality of the dimension. So in other words, L is equal to A plus Fy. But we get a couple of things out of this. So one thing that we get is that A is an ideal. And A is an ideal because it satisfies this absorption property of the bracket. But notice the absorption property of the bracket is pretty trivial here because we just have one more vector to check, and that's this vector y that we've been working with. Another thing that we see is that the dimension of A is equal to, well, 1 less than the dimension of L, but the dimension of L was k plus 1, so the dimension of A is k. But let's recall that little claim that we've been proving this whole time, which was that L had an ideal of dimension 1 less than the dimension of the whole Lie algebra. But that's exactly what we've done here. So what did we do so far? We had a k plus 1 dimensional Lie algebra L. And what we did is showed that the maximal subalgebra had dimension k. It was also an ideal. And we were able to thus decompose L as follows. And that is that L was equal to A plus Fy. And again, we have a couple of things here important, that the dimension of A is k and that A is an ideal. But since the dimension is k, which is in the induction hypothesis realm, we can apply the induction hypothesis to A. But what does that give us? Something which I'll call U, which is non-zero inside of V, such that A of U is equal to 0 for all A in A. So again, that's just applying the fact that the result holds for all Lie algebras of dimension k and less. And now to move forward, we want to look at the other way of realizing this, and that is as follows. So the intersection, as we go over all A in A, of the null space of A is a non-zero subspace. So I'll call that non-zero subspace W. So just in terms of this right here, that means this element U is inside of this W. And now, since Y is inside of L, and L is inside of GLV, we can view Y restricted to W as an element of GLW. So that's just, we're looking at Y acting on the elements of W instead of the elements of the whole vector space V. Okay, but note that Y is a nilpotent linear transformation. But since it's a nilpotent linear transformation, it has a non-zero vector in its kernel. But that means its restriction also has a non-zero vector in its kernel as well. So that means there exists a vector which is non-zero, which I'll call W within W, such that Y evaluated at W is equal to 0. And now I'm going to claim that this vector W is the vector we've been searching for the whole time. So let's take an arbitrary X inside of L. So this is completely arbitrary. But notice that we can write X as something inside of A plus alpha times Y, given this decomposition right here. And let's just point out that A comes from the subalgebra capital A and alpha comes from the ground field F. But now let's observe, if we take X evaluated at W, we get A evaluated at W plus alpha times Y evaluated at W, but all of that just like cancels all the way down to W for a variety of reasons. The first reason is, well, it's the way that we constructed this subspace capital W as the intersection of the kernels of all of the A's, and then applying that previous result to get further something within the kernel of Y. But that's exactly where we needed to end up, because what do we have? We've got this non-zero vector here inside of what we have is W, but that's a subspace of V, such that if you plug it into any linear transformation X from L, you get 0. But looking over the statement of the lemma, that's exactly what we wanted. Now we're ready for the proof of our main theorem. Okay, now we're ready to prove Engel's lemma, the main result of the video. So let's recall what it says. So we want to suppose we've got a Lie algebra, which is a subalgebra of the Lie algebra of linear transformations of a vector space V, where V is finite dimensional. And then we also want to suppose that every element L viewed as a linear transformation from V to V is nilpotent. Then we can get a basis B of V such that the representation of every element of the Lie algebra within this basis is a strictly upper triangular matrix. Okay, so the first lemma we did showed that if we had a single nilpotent linear transformation, we could express that as a strictly upper triangular matrix. This says that if we've got an entire Lie algebra of linear transformations that are nilpotent, we can simultaneously express them all as strictly upper triangular matrices. So that's what's interesting and powerful about this. Okay, so the proof will be induction on the dimension of L. That shouldn't be a surprise. That's what we've been doing for these other proofs. So the base case, well, that's n equals 1, but that's pretty much the first lemma. There's not really anything else to do there. So now let's do our induction steps, starting with an induction hypothesis. So suppose for all Lie algebras of dimension less than or equal to k, the statement holds. And then, well, we want to set up the next part, which is, let's also suppose that the dimension of our Lie algebra in question is k plus 1. And now let's get to applying our preparatory results. So by the exact previous statement, and this is the one that we just finished, there exists a V within V such that X evaluated at v is equal to 0 for all x inside of the Lie algebra. And the important thing here is that this is a non-zero vector v. So in other words, this vector v is within the intersection of the kernel of all of these linear transformations. Okay, great. And then what we want to do from there is set U equal to the one-dimensional vector space spanned by this vector v. And actually, I'm going to change this v to a u, just like to make it more in line with the notation we're using. So u is the span of this single vector u. Great. And then now we want to build a diagram that will help us apply the induction hypothesis. So let's do that. So for all x in L, consider the following diagram. So on the top, we'll have v, and v will be mapped to itself via x. And then here we're going to project again down to v mod u. So that's happening on both sides. So v mod u. And then across here will be our map x bar. So this is essentially the same picture that we had on a previous result. And how does this x bar work? Well, it's applied to a coset v plus u and gives us x evaluated at v plus u. So it gives us that coset. But notice under this picture, we can view L as being pushed inside of the Lie algebra GL, let's see, v mod u, where every x inside of L turns in to this x bar map down here. And furthermore, this map here is a Lie algebra homomorphism. I won't prove that, but that's pretty easy. And then let's introduce some more notation. Let's say that L bar is the image here. So it's every x bar as x runs through all elements of L. So it's like the version of the linear transformation x when applied via this quotienting diagram here. But let's note that the dimension of v mod u is equal to k, which is, well, less than or equal to k. But that means we can apply the induction hypothesis. But that induction hypothesis gives us a basis, which I'll call B, of v mod u that, well, it does this thing of simultaneously strictly upper triangular matrices. So let's write down this basis. So let's say it's v1 plus u all the way up to vk plus u. So of course, the vector space is a quotient vector space, so its elements are cosets. So that's why I've written it like that. And again, this satisfies the rule that for all x bar inside of L bar, the matrix representation of x bar with the basis b bar is upper triangular. Okay, good. But next up, we want to set just b without the bar equal to the set u and then v1 up to vk. But then, since we know that x evaluated at u is equal to 0, that was like kind of the point of u over here, that means that x inside of this basis is upper triangular. Now, I've skipped a couple of little steps here, but these steps that I've skipped are essentially the same thing that we did earlier, where we wrote that upper triangular condition as being spanned by certain vectors. Okay, but notice that this holds for all x inside of the Lie algebra, so that does it. We've got all x are represented by strictly, and this should be strictly also, upper triangular matrices simultaneously. Okay, so now let's look at a second version of Engel's theorem. So today we've been working with nilpotent maps, and in a previous video we also worked with nilpotent maps, but we also worked with nilpotent Lie algebras. And the second version of Engel's theorem ties these two together. And so it says that if we've got a Lie algebra L, L is nilpotent if and only if every element of L, x, its adjoint map is nilpotent. Okay, so let's see if we can prove this. So it's an if and only if statement, which means we have two directions to prove. Let's do the first direction. So let's suppose L is nilpotent. But let's recall what that means. That means that there exists a capital N, which is a natural number, such that this thing which was L upper N with no parentheses for some reason was equal to 0. And let's quickly recall what L upper N was. So L upper 1 was the bracket of L with L. And then after that, we defined L upper N plus 1 as the bracket of L with Ln. So that inductively defines these L upper numbers here. Okay, so now let's take an x and y inside of L, and we want to work towards this. And we're going to work towards this as follows. So let's look at the repeated bracketing of x with y. So let's say we've got x, x, bracket x, all the way down in the bottom we have bracket x, y. Then this comes all the way out. So let's notice that if we choose the appropriate number of brackets here, this will be inside of Ln. But Ln was 0 by the fact that L was nilpotent. But let's also notice that this is the adjoint map of x applied n minus 1 times to y. But this happens for any y for sure. But since this happens for any y, that means the adjoint action of x to the n minus 1 power is the 0 map. But that being the 0 map means that it's nilpotent, which is what we needed over here. Okay, let's do the reverse direction. Okay, so now for the reverse direction, we'll start with the assumption that add x is a nilpotent map for all x within the Lie algebra L. And then we want to consider the following map. So I'll call it the add map, and it goes from L to GLV. And well, what does it do? Well, it takes an element x and it sends it to add x. And this is a Lie algebra homomorphism. And the fact that this is a Lie algebra homomorphism follows from the pretty simple calculation that the bracket of add x, add y is the bracket of add, or sorry, it's add bracket x, y. Okay, then let's let L tilde equal the image of this adjoint map inside of GLV. And then we'll apply Engel's theorem to the image, this L tilde. But what that means is that we can find a basis so that add x represented in this basis is strictly upper triangular. So in other words, it looks like this. So it'll have zeros on the diagonal, and then it can have like these non-zero things above the diagonal, and then of course 0 below the diagonal. And then I'm just going to finish it in words, and one of the exercises will be to make this a little bit more careful. So the result follows just from the fact that when you commute matrices like this, you end up pushing the 0 maybe diagonals up and right. So if you commute two matrices like this, then you'll get another diagonal of zeros. Well, and then that kind of thing continues on and on and on until you've got just a matrix of all zeros. Okay, so that finishes the proof of the second Engel's theorem. Now I'm going to leave you with some exercises. Okay, so now two exercises. The first is to finish the last proof carefully. So this bit about pushing the zeros up and right. The second one, we want to suppose that L is a Lie algebra over the complex number, so that's our base field. And then show that L is nilpotent if and only if every two-dimensional Lie subalgebra of L is abelian. And that's a good place